Hello, we are Group 5 and today we will present to you the solution for question 1 and 2 in our fixed income group assignment. First, let me briefly introduce question 1. Madison Manufacturing has a series of future liabilities at different maturities, specifically at year 3, 5, 7, and 9. The goal is to evaluate these liabilities and then construct a bond portfolio that can immunize them against the interest rate risk using duration and convexity. Now, moving to part A. In this part, we calculate the price, duration, and convexity of the liability, assuming a flat yield curve of 10%. First, we discount each liability cash flow using the zero coupon bond with a face value of $1 formula, which is 1 over 1 plus the yield raised to the power of the maturity. By multiplying each cash flow with its discount factor, we obtain the present value of each payment, and after assuming all discounted cash flow, the total liability value is approximately $14.27 thousand. Next, we compute the Macaulay duration, which represents the weighted average timing of the cash flow. The result is about 5.68 years. We then adjust this to obtain the modified duration, which measures the sensitivity to interest rate changes, which is approximately 5.16 years. Finally, we calculate the convexity, which captures the curvature of the price and yield relationship. The liability convexity is around 36.44, with modified convexity about 34.81. This measure will serve as a benchmark for constructing an immunized portfolio in the next part. Now, moving to part B. Here we evaluate each bond in terms of price, duration, and convexity using the same discounting approach. For each bond, we calculate the present value of its coupon and principal payment, then derive the duration and convexity based on the weighted cash flow. From the summary table, we observe the following key results. The bond 1 has the lowest duration, around 2 years, while bond 5 has the highest duration, approximately 6.78 years. This allows us to classify those bonds into two groups. Bond 1, 2, and 3 are short duration bonds, while bond 4 and 5 are long duration bonds relatively to the liability duration of 5.68. So this distinction is important because to match the liability duration, we typically need a combination of short and long bonds. Now moving to part C, which is the core of the problem. Our goal is to construct a bond portfolio that satisfy Reddington immunization. This requires three conditions. First, the asset value must equal to the liability value. Second, the duration of the asset and liability must match. And third, the convexity must be greater than that of the liability. And because there must be no short selling, the value of each bond cannot fall below zero. To solve this, we first set up a system of equations based on price and duration. Using Gaussian elimination, we reduce the system and express two variables in terms of the remaining three. So this showed that the system had infinitely many solutions since there are five variables but only two equations. And to obtain the feasible solutions, we consider the basic portfolios where we select only two bonds at a time and set the remaining variables to zero. For each pair of the bonds, we solve the system and check for two conditions. First, the non-negativity or the no short selling condition, and secondly, the convexity condition. From the result, we obtain six valid portfolios of vertices, such as the combination of bond 1 and bond 4, or the combination of bond 2 and bond 5, and so on. Each vertex represents a feasible immunized portfolio consisting of only two bonds. Importantly, since the constraints are linear, any combinations of these vertices will also satisfy the conditions. In other words, all feasible portfolios can be constructed by mixing these vertices, so there are infinite answers to this problem. And for the remaining parts, I would like to hand it over to my teammates.
Now I will present part D and E, where we optimize portfolio convexity under reductant immunization. For part D, our objective is to maximize portfolio convexity while still satisfying the two reductant conditions. The present value of assets must equal the present value of liability, and the duration of assets must match the duration of liabilities. In addition, we impose a non-negativity constraint, meaning that short selling is not allowed. Using Excel solver, we set the objective to maximize modified convexity with the decision variables being the face value of the five bonds, subject to the present value matching and duration matching constraints. From the optimization results, we find that the optimal solution invests only in bond 1 and bond 5. This creates what is known as a barbell structure, combining a very short maturity bond with a very long maturity bond. This structure maximizes convexity because convexity increases with the dispersion of maturities. By allocating weight to the two extremes of the maturity spectrum, we maximize the curvature of the price-yield relationship. As a result, the portfolio convexity reaches 41.97, which is significantly higher than the liability convexity of 34.81. So that is how we do in Excel solver. In terms of surplus intuition, under reductant immunization, the surplus is driven by a second order effect. Duration matching eliminates first order interest rate risks, so the remaining effect comes from the difference in convexity. Since asset convexity is greater than the liability convexity, the surplus remains non-negative when yields change. For example, when the yield drops to 1%, the surplus increases to approximately 0.75 million. The surplus curve is strongly U-shaped, indicating strong protection against large interest rate movement. So moving to part E, we now minimize convexity under the same constraint. Using solver again, but this time minimizing the objective, the optimal solution invests in bond 3 and bond 4. This results in a bullet strategy where cash flow are concentrated around the liability horizon, and the resulting convexity is 36.57, which is only slightly higher than the liability convexity of 34.81. So in this case, the surplus curve is still convex and non-negative, so immunization still holds. However, the curve is much flatter. For instance, when the yield is 1%, the surplus is only about 0.16 million, which is significantly smaller than in the maximum convexity case. Overall, Part D produced a barbell strategy with high convexity and strong protection, while Part E produced a bullet strategy with lower convexity and a smaller protection cushion.
So now I will compare the two strategies in terms of risk and performance. So the first strategy is the barbell portfolio, which is combined bond 1 and bond 5. This portfolio has a convexity of 41.97, resulting in a convexity gap of 7.16 relative to the liability. And this large convexity gaps produce a step U-shaped surplus curve, meaning that the portfolio generates significant gains when interest rate moves substantially. So, however, the strategy also has a drawback. It is more vulnerable to non-parallel shifts in the yield curve, such as twist, steepening, or flattering. Because the cash flow are distributed at the extreme, so the second strategy is the bullet portfolio, which combine bond 3 and bond 4. This portfolio has a convexity of 36.57, which is a much smaller convexity gap. As a result, the surplus curve is flatter and the gains from interest rate movement are more limited. For instance, under the same yield change scenario, the surplus is only about 0.16 million. This implies a smaller protection cushion, but the strategy is more stable. Its key advantages is that it is more robust to changes in the shape of the yield curve, since the cash flow are concentrated around the liability timing.
So now let's move to question 2 is about the yield curve constructions and fixed income derivative pricing. So in part A, it's required us to calculate the spot rates and to
from maturities from 1 to 20. So as shown from the table, for missing data point, we use the linear interpolation. This formula allows us to accurately estimate the rate span two nearest known data points. So for example, at year 4 is we between year 3 and also year 5. So we're gonna apply the formula and we're gonna have the data for year 4 and the rest of this. So after, so in the next question is part P. It's requires to calculate the zero carbon bonds. We already have the formula is one divided by one plus spot rate to the power of t, where st is the spot rate for maturity t. So when we apply the formula, we're gonna have the answer for 20 years from year 1 to year 20, which directly reflects the time value of the money. And next for part C, it's required to draft the swap rate curve and forward rate curve. So before we can do it, we have to calculate it by using the formula what we have learned about forward rate and swap rate. After applying this rate, we're gonna have the outcomes is for the year 1 to year 20. The forward rate is derived from the spot rate representing the market expectations of the future interest rates, and while the swap rate is calculated by equating the present value of the fixed and the floating rates in the plain vanilla interest rate swap using the zero coupon bonds as a discount factor, and this data show both the forward rate and the swap rate. So after have the data, we're gonna draft the curve where to visualize the perspective. So this graph highlights three core characteristics of the term structure. For the spot rate curve, which is the blue one, it is upward sloping. This indicated longer maturity requires a higher premium to compensate for the duration risk. This one is for forward rate curve, is the yellow curve. So because the spot rate curve is rising mathematically, so the forward curve must lie above it. And next one is for the swap rate curve, is the red one. Is the line is lines between below the spot rate and also the forward rate, and it represents the fair fixed rate is generally averaging the interest rate expectation over the life of the swap contract. So now let's move to part D. It requires to calculate the price of European call and put option. So when we have we already have the data from the information. So now when we have the data, we're gonna conduct the main four calculations in order to find the price. So first the bond price, we use the data and we apply the formula in on the slide to have the data. The bond price equal to 1,029 1,029 mm, uh, 29,392. We also use the similar with the formula for the modified duration, which is approximately 4.3 years. The forward yield is 4.480%. The price volatility we base on the modified durations and about the yield volatility in the so the price of the bond is about 1.97%, and the forward bond price is 1,088,883. So after we have calculated this, so we're gonna apply this number to calculate for the D1 and D2, which is very essential to calculate the European call and put option. So after we apply the formula, we got D1 is equal to 0.04 and D2 is minus 0.001. So after applying the formula for the put and call option, we got the result is for the call option is 14 millions 88 40,884, and for the European put option is 14 154, and that's all. And next one is for the part E and F presented by friend.
Now I will present how we price the callable and puttable bonds and then analyze their spreads. The key idea is to separate the bond into straight bond and embedded options. So for part A, which is callable bond, first we calculate the value of straight bond This is done by discounting on coupon payments and the final principle using spot rate curve derived earlier, and the results are the yellow line. Next, we consider the embedded call option. This option gives the issuer the right to redeem the point at year 5. We value this option using black model, where the underlying is the forward bond price at year 5 and the strike is the call price, and we calculate it in Part D with the value of 14,884.45. After obtaining the option value, we subtract it from the straight bond price. So overall, the callable bond is lower than the straight bond. This is because the call feature the benefits the issuer and create investment risk for investor when the interest rate fall. So for the putable bond, the process is very similar, but the perspective is reversed. We again start with the straight bond price using the same discounting approach. Then we value the embedded put option using the back models, which is the result in Part D of 14,154.22. So instead of subtracting, we now add the put option value to the straight bond price. As a result, the puttable bond is more valuable than the straight bond. This is because the put option provided protection against rising interest rate, which would otherwise reduce the bond price. So after obtaining the bond price, we move to the spread analysis. First, we compare the yield to maturity for both bonds. This is the cap rate that makes the present values of the cash flow equal to the bond price. Next, we calculate the G spread, which is the difference. Uh, Next, we calculate the G spread, which is difference between the bond yield and the 10-year government spot rate. Then the I spread compare the bond yield with the 10-year swap rate, which reflect the market funding conditions. For the yes spread, the approach is slightly different. We add a constant rate to our spot rate and use the Excel solver to adjust the spread until the discounted cash flow matches the bond price. Finally, we verify the result by recomputing the present value using the yes spread. As shown in the table, the recalculated value matches exactly with the bond price, confirming the accuracy of the method.